Imagine the skies each fall, teeming with billions of birds embarking on a monumental journey. As temperatures plunge and food sources vanish in the north, these birds, driven by survival, head south in a mass exodus. But what triggers this epic migration? And how do these birds master such an arduous journey year after year? The first dramatic scene unfolds with the formation they choose, the V shape, a masterclass in aerodynamics and energy efficiency. Each bird, by flying just above the one in front, reduces wind resistance for the others. This not only conserves energy, but allows them to cover long distances without fatigue. But who leads this formation? Surprisingly, there's no permanent leader. Instead, when the lead bird tires, it rotates back, and another takes its place. This democratic system ensures that no single bird bears the full brunt of the wind during their long journey. But how do these avian navigators find their way across continents and oceans? The process is complex and involves a variety of cues and sensory inputs that birds integrate seamlessly during their journeys. During the day, birds use the position of the sun to orient themselves. This method involves an internal clock that adjusts for the changing position of the sun throughout the day, helping them maintain a consistent direction. At night, many species of birds switch to stellar navigation, using constellations to guide their path. This celestial navigation was confirmed in experiments showing that birds under planetarium skies can orient themselves by the stars alone. Moreover, birds are equipped with a fascinating ability to tap into Earth's magnetic field, acting like a natural GPS. This magnetic sense, or magnetoreception, involves specialized photoreceptors in their eyes, or magnetite particles in their beaks, allowing them to detect magnetic fields. This ability enables them to determine their latitude and longitude, essential for long-distance travel across featureless areas like oceans. Adding to their impressive suite of navigational tools, some species utilize polarized light patterns in the sky, a technique that even works when the sun is obscured by clouds. Additionally, they use visual landmarks such as mountain ranges, rivers, and coastlines, especially near their starting points and destinations. Research has also indicated that birds might use olfactory cues, detecting smells associated with specific locations to help them navigate. The precise mechanisms of how birds combine. These different navigational tools are still a subject of ongoing scientific research, offering a compelling glimpse into the complex interplay between biology and the natural world. You might wonder, how do they know exactly when to leave and when they have arrived? Birds respond to a mix of environmental signals, such as temperature changes and food availability, which cue them to start or end their migration. It's a finely tuned instinct that tells them when conditions are right. Now, consider the extraordinary energy requirements it takes to fly thousands of miles. The physical demands of migration are immense, and birds prepare for this arduous journey with meticulous care. Before departure, many species undergo a physiological transformation, entering a hyperphagic state where they increase their food intake dramatically. This is not merely eating more. It's a strategic accumulation of energy reserves. They primarily store fat, a dense energy source, which provides more than double the calories per gram compared to carbohydrates or proteins. This fat is crucial as it metabolizes into energy during the long flights, sustaining them when food is not available. As they traverse vast landscapes and oceans, these avian migrants also show remarkable savvy in their travel plans. Along their migratory routes, they make strategic stops at key locations known as stopover sites. These are not random choices, but are rich in food resources, providing critical refueling opportunities. For instance, shorebirds often stop at wetlands teeming with invertebrates, while raptors may target areas with abundant prey like small mammals. These stopover sites are akin to pit stops along a highway, indispensable for the birds to replenish their energy reserves. Interestingly, the locations of these stops are often passed down through generations, with young birds learning from their elders during their first migrations. Research also shows that some birds can adjust their route mid-journey, seeking out new stopover sites in response to environmental conditions, such as weather changes or food availability. Despite the bountiful resources and warmer climates in the south, why don't these travelers stay year-round? The answer lies in the North's springtime bounty. The return journey is timed with the explosion of insect populations and the availability of nesting sites, conditions that are perfect for breeding and raising their young. As the harsh winter recedes, it gives way to a surge in insect populations, crucial for feeding hungry chicks. This explosion of food availability is no small event. It includes not only insects, but also a variety of burgeoning plant life that supports other forms of wildlife, creating a rich food web essential for the nourishment of young birds. Additionally, the northern territories, being less crowded during this season, offer ample and prime nesting sites. Furthermore, the lengthening days provide longer periods of daylight, allowing more time for parents to forage food for their offspring, thus increasing the survival rates of the young. The number of migratory trips a bird undertakes in its lifetime is closely tied to its lifespan and the frequency of its migrations. Small migratory birds, which often face harsher conditions and higher predation rates, may make a significant number of migrations in their shorter lives. For example, a typical small migratory bird, like the Swainson's thrush, might undertake up to 10 to 15 round-trip migrations if it reaches the upper end of its lifespan. Each round trip can cover thousands of miles from North America to South America, representing a remarkable achievement for such a small creature. On the other hand, larger migratory birds, which generally have longer lifespans, might undertake fewer migrations annually, but continue over many more years. For example, the Arctic tern, known for the longest migratory distance of any bird, travels from its breeding grounds in the Arctic to the Antarctic, and back again each year. While Arctic terns are not particularly large, their robust lifespans of up to 20 to 30 years allow them to possibly accumulate migration distances equivalent to traveling to the moon and back over their lifetimes. Some species, perfectly adapted to their environments, remain in the northern regions throughout the year, braving the cold and scarcity of food that winter brings. These resident birds have developed unique adaptations that allow them to thrive in harsh conditions. One prominent example is the black-capped chickadee, a small, resilient bird commonly found in North American forests. The black-capped chickadee does not migrate southwards, but instead faces the winter head-on. It has several adaptations that enable it to survive the frigid temperatures. Physiologically, it can regulate its body temperature, lowering it during cold nights to conserve energy in a state known as torpor. Behaviorally, it has an excellent memory for locating food caches it has hidden away during more abundant months. These caches are crucial for winter survival when food sources are scarce. Each migration season adds to our understanding of these creatures' complex behaviors. Studies show that migratory birds are not just moving between feeding and breeding sites, but are also crucial for ecosystems, aiding in pollination and pest control, which benefit agricultural areas and natural habitats alike. This annual journey is not just a survival tactic, but a significant ecological event that underscores the interconnectedness of our global ecosystem. As you watch these birds glide across the horizon, consider the profound mysteries of nature they represent. Each wing beat a story of survival, and each flight path a testament to intelligent design. Subscribe for more answers to a million silly questions.